Welcome back to Grand Structures. This is the Burj Khalifa. It is the tallest thing humanity has ever built. A single, shimmering spire that punctures the sky above Dubai at a staggering 2,717 feet. That's nearly 830 meters tall. This structure is so tall, you can watch the sunset twice from it. Once from the base, and then again just a few minutes later after taking the elevator to the top. It's not just a building, it's a testament to human ambition, a symbol of a nation's vision, and a marvel of modern engineering. But to understand this building, you first have to understand the vision behind it. In the early 2000s, Dubai was at a crossroads. Its economy was built on oil, but its leader, Sheikh Mohammed, knew that the oil would one day run out. He had a radical vision to transform Dubai from a regional oil hub into a global destination for tourism, finance, and innovation. To do that, he needed a landmark, an icon so bold, so unmistakable that it would put Dubai on the world map and announce its arrival on the global stage. The developer, Emaar Properties, was given a simple, audacious brief: build the tallest building in the world. The challenge fell to the legendary American architectural firm Skidmore, Owings and Merrill, or SOM. The lead architect, a man who had already designed some of the world's super talls, Adrian Smith. But from day one, the entire team faced a central, fundamental problem, a problem that defines this structure. How do you build a tower of this scale in the middle of one of the hottest places on Earth? Dubai's summer temperatures can soar to 122 degrees Fahrenheit or 50 degrees Celsius. The sun is relentless. If they built a standard glass tower, it would become the world's tallest greenhouse. The air conditioning costs alone would be astronomical, making the building financially and environmentally unviable. It would be an uninhabitable furnace. The building's height was a structural challenge, but its survival was a thermal one. The architects had to find a way to create a skin, a suit of armor, that could defeat the sun. The solution is this: 26,000 custom-built, high-performance glass panels covering an area of 1.2 million square feet. That's the size of 5 football fields. And the story of how this glass is made, from simple sand to a high-tech shield, is one of the most fascinating parts of this entire grand structure. Every piece of glass, from a simple bottle to a skyscraper panel, starts as sand. But here is the first great irony of the Burj Khalifa. They couldn't use the sand from the surrounding desert. It seems impossible, right? A tower built on sand in a sea of sand had to import its sand. The reason? Desert sand is aeolian, meaning it's been eroded by wind. Its grains are too smooth and too rounded to bind correctly. For high-quality glass, you need special, high-purity, low-iron silica sand, which was imported from other regions. A simple but critical first step. This high-purity sand, along with soda ash and limestone, is fed into a colossal furnace and melted at over 2,700 degrees Fahrenheit or 1,500 degrees Celsius. It becomes a glowing, molten lava. But how do you turn this 2,700-degree liquid into a perfectly flat, perfectly distortion-free sheet of glass? You use one of the most brilliant inventions of the 20th century, the float glass process. The molten glass is poured from the furnace in a continuous, fiery ribbon onto a perfectly flat, perfectly shallow bath of molten tin. The glass is lighter than the tin, so it floats on top, just like oil on water. The molten tin is incredibly smooth, and gravity pulls the glass flat as it spreads across the surface. This river of glass, dozens of feet wide, slowly moves down the line, gradually cooling in a long tunnel called an annealing layer. This controlled cooling process is critical. It removes internal stresses from the glass, preventing it from shattering. At the end of this process, we have a perfectly flat, perfectly clear, giant sheet of float glass. But this is just normal glass. It's not strong enough, and it offers almost no protection from the sun's heat. To become armor for the Burj Khalifa, it needs superpowers. The first superpower is its invisibility shield. The panels are sent into a massive vacuum chamber for a high-tech process called magnetron sputtering. Inside this chamber, almost all the air is pumped out, creating a near-perfect vacuum. Then, using powerful magnetic fields, the machine sputters or blasts microscopic particles, literally atoms, onto the surface of the glass. Layer by layer, atom by atom, a coating is built. This coating is incredibly complex and impossibly thin, thousands of times thinner than a human hair. For the Burj Khalifa, they used a double silver coating, which means 2 microscopic layers of silver surrounded by other layers of metal oxides. This coating is a miracle of physics. To visible light, it's almost perfectly clear, letting in the stunning views. But to solar radiation, the heat, it acts like a mirror, reflecting a huge portion of it away from the building. It's a one-way mirror, but for heat itself. Okay, so now our glass is a high-tech sun reflector, but it's still just as brittle as a window in your house. At 2,000 feet, where winds can gust over 90 miles per hour, that's not good enough. It needs to be incredibly strong. It needs its second superpower, tempering. To temper it, the glass is heated again to over 1,100 degrees Fahrenheit, almost to its softening point. And then, at the precise right moment, it's quenched, blasted with powerful, high-pressure jets of cold air. This thermal shock cools the outer surfaces of the glass much faster than the inside. This differential cooling creates a state of incredible internal stress. The outer surfaces are locked in a state of high compression, while the inner core is in tension. These opposing forces are what give tempered glass its incredible strength. It's now 4 to 5 times stronger than the original float glass. And as a bonus, if it does break, it doesn't create sharp, dangerous shards. The stored-up energy causes it to shatter into thousands of small, safe, pebble-like crumbs, a critical safety feature for a public skyscraper. So now we have our 2 main components: a strong, tempered inner panel and a sun-reflecting, coated outer panel. But the final piece of the puzzle is to combine them into the glass sandwich, what engineers call an insulated glass unit, or IGU. This is the final brilliant step. The 2 panels of glass are not pressed together. They are held apart by a spacer bar. This bar is crucial. It's filled with a desiccant, a material that absorbs any water vapor to ensure that the panel never fogs up from the inside. The gap between the 2 panes is then filled with an inert gas, usually argon. Why? Argon is a much worse conductor of heat than regular air, adding another powerful layer of insulation. It's like a thermal winter coat for the building. Finally, the entire unit is sealed with a primary and secondary sealant, creating a perfectly airtight, moisture-free, high-performance shield. This is the armor of the Burj Khalifa, a panel that lets in light but blocks heat, a panel that's strong enough to withstand desert winds but safe enough for a public space. Now, all they had to do was make 26,000 of them and install them. While the glass was being perfected in factories, the tower itself was rising at a record-breaking pace. At its peak, this was a vertical city with over 12,000 workers and engineers from more than 100 countries on site every single day. The logistics were mind-boggling. Installing the glass facade, or curtain wall, was a masterpiece of choreography. Each 300-pound panel had to be lifted by a series of specialized cranes and building maintenance units, or BMUs. These are the same machines that would later be used to clean the windows. Teams of highly skilled installers working in the extreme heat and wind would guide each panel into its precise location on the building's aluminum and steel frame, panel by panel by panel. A giant 26,000-piece puzzle assembled hundreds of feet in the air. This installation process alone took over 2 years to complete. But this leads to the question I know you're all asking. After all that work, how on earth do you clean it? You can't just call a local window washer. The Burj Khalifa is cleaned using 18 custom-built, multi-million-dollar machines. These BMUs are hidden in special garages within the building structure. When not in use, they are completely invisible. When it's time to clean, giant doors open and these telescoping armed machines emerge, carrying a basket with a team of cleaners. The machines are state-of-the-art, but the cleaning itself is old-fashioned. Soap, water, and a squeegee. A team of over 30 dedicated cleaners works year-round. And get this, by the time they finish cleaning all 26,000 panels, which takes about 3 to 4 months, it's time to go right back to the beginning and start all over again. It is a literally never-ending job. But the genius of this grand structure has one final brilliant secret. In Dubai's hot and humid climate, a massive amount of condensation forms on the chilled surface of the glass every day. The engineers didn't see this as a problem, they saw it as a resource.
They designed a condensate collection system. All that moisture is gathered, channeled into a massive reservoir, and then used to irrigate the beautiful parks and gardens at the tower's base. The system collects about 15 million gallons of water a year. That's enough to fill 20 Olympic-sized swimming pools. The Burj Khalifa literally drinks from the desert air, using its own armor to water the oasis at its feet. The Burj Khalifa is so much more than just the world's tallest building. It's a symbol of a vision, a story of how a city and a nation dared to build an icon that would defy its climate and announce its place in the future. From the myth-busting sand, to the atomic-level sputtered coatings, to the high-strength tempered sandwich that insulates and protects, its glass armor is a masterclass in materials science. It's what makes this building possible. It's what allows this grand structure to stand in the sun, not as a furnace, but as a glittering beacon of human ingenuity. What grand structure should we cover next? Let me know in the comments below. And if you loved this deep dive into the engineering, be sure to subscribe to Grand Structures and hit that bell so you don't miss our next story. Thanks for watching.